Good morning everyone. Thank you for joining Mr. Ish for this video on complex numbers. A continuation from the previous set of videos I've done on complex numbers and imaginary numbers. If you remember, I've presented a video on imaginary numbers where we discussed in a very basic manner the concept of this imaginary number I. Then the next video we went ahead to talk about complex numbers such as this form x plus yi, where there was a real part to this complex or composite and there was a imaginary part. So this right here, z equals x plus yi, or you can say iy, however you want to write that. This here represented your basic complex number, which had the x representing the real part and the yi representing your imaginary part. And then in that same video I talked about how we can determine the r, which is your modulus. If you look over here on this complex plane, the x-axis represented the real axis and the y-axis represented your imaginary axis. For any complex number that you were given, you could break it down into a coordinate form. Remember, something which looked kind of like x comma y, and then we were able to easily plot it and then determine your modulus, which represented your r. The modulus was basically just employing the Pythagorean formula a squared plus b squared equals c squared, except here we're using x, y and r. In addition to that, we determined the angle by using the arctan formula. It was the arctan of your opposite or adjacent, or y or x, which is the tangent formula. And then we went on to rewrite in a very basic manner. X could be easily represented as r cosine theta, which was the cosine function formula, and y was equal to r sine theta, which was the sine function formula. But when we looked at this form over here and then we looked individually at what x and y were, we were able to combine them together into this revised version. The revised version could be isolated for r and then presented in this polar form. R multiplied in parentheses by cosine theta plus I sine theta. Remember, this I called in the previous video the polar form. But in many books it is also called the trigonometric form. So anytime a question says that you have to convert this form into trigonometric form, they mean the polar form. Polar form and trigonometric forms are synonymous. Lastly, I also mentioned in the previous video that this form right here, the basic form of the complex number, and the polar or the trigonometric form were interchangeable. That is, if you open this, you'd end up with this. But you could take the basic form and convert it into the trigonometric form by calculating the modulus and the argument. Remember, this here represented the argument. So this set of series over here represented a means for converting this form into the trigonometric form, but you could also work backwards and convert the trigonometric form or the polar form back into the basic form of complex numbers. Again, symbolized with the letter Z. I want to show a single example of this interconversion before we delve into the main aspect of this video. The main aspect of this video will be talking about the operations of the complex numbers, namely the multiplication of polar forms and the division of polar forms. It's going to be one step in terms of higher difficulty than what we've presented, but this video over here will serve as the direct precursor to our last video on complex numbers, where we talk about a very specific and important theorem when it comes to polar complex numbers. As a very good review, we're going to look at this trigonometric or polar form of a certain complex number. Our goal over here is to show you very quickly the conversion of this form into the basic form. Then we'll very quickly show the basic form and convert it back into this form. It will not be hard. But very quickly on the start, what we want to do is recognize a couple of items over here. We want to look at what r is, and we want to identify what our angle is. You know, r over here is root 8, and we can write root 8 as 2 root 2 because square root of 8 is 2 root 2. But another important task over here is to also identify what minus pi over 3 means. And you know, minus pi over 3 comes from a angle. If you look over here, it's my 360 or my 0 degree line. If I'm going minus 60, remember, minus means clockwise. I'm going minus 60 degrees down this direction. I'm going to end up with a 300 degree angle. Right? I'm going to end up with 300 degrees. What is 300 degrees going to be? It's going to be 5 pi over 3. So let's just put this 5 pi over 3 over here on the side in case we have to come come back to it and use it. So we just dissected here what minus pi over 3 will be, and it'll be 5 pi over 3, and we have our modulus over there. So the argument and the modulus are both laid out in front of you. What we need to do is basically open this up. 5 pi over 3, let's look at that in terms of a trigonometric ratio. If this is my 300 degrees or 5 pi over 3, you know it's a 60-degree reference angle. You know you're going to have a root 3 over here, and you're going to have a 1 over here, and you'll have a 2 over here. What's the cosine of 60 degrees, which is minus 60, or 300 degrees going to be? It's going to be 1 over 2. See, my cosine value will be 1 over 2. But what my sine value is going to be, is going to be minus root 3 over 2. The only reason why I put this extra step ahead of you is because I need to know what these values are. I want to try doing all of this without using a calculator, just to show you how knowing some of these basic fundamentals helps. All we got to do is actually open it up, given what we've laid down over here. Z is equal to 2 root 2 cosine of minus pi over 3, cosine of minus 60, or cosine of 300 is 1 over 2, plus I. Sine of the same is a minus root 3 over 2. Minus root 3 over 2 means it's going to negate this positive and make it a minus. Want it? You'll still keep the I. All you got to do is now open it up. Look at these 2's in the denominator and this 2's in the numerator. Cancel them out. They will cancel out. On the top you'll get, as you open the parentheses, root 2 minus I root 6. Now what you've done is converted your polar trigonometric form into the basic form right here, x plus yi, x plus yi. As I said, I want to show you the interconversion of this back, and I want to do that. I wanted to show you that these polar forms and the basic forms are interconvertible easily. The only thing you need to know are the modulus and the argument. Once you know those two aspects, you can easily interconvert. Look over here. Imagine the question is this. Now you have to convert this back into your polar or trigonometric form. As I showed you in the previous video, the first and the best thing to do is to plot it out in terms of having a set of coordinates. Root 2 minus I root 6 looks something like this. Minus root 6. Why do you want to put it in x comma y form? Because it shows you which quadrant you're in. You're in a quadrant where the x value will be positive, but the y value will be minus, and that means quadrant number 4. Not drawn to scale, you'll end up somewhere over here. Draw it over here. Connect it, and here's your r, here's your theta, here's your x, here's your y. You know what your r value is, you gotta calculate it, but I already did that before. It was a 2 root 2. It would be root 2 square plus root 6 square root, and you'll get root 8, which is 2 root 2. So I know my r is a 2 root 2, but I've already calculated the 5 pi over 3. And you could have calculated 5 pi over 3 this other way. Remember, over here you can calculate it this way. Theta is equal to arctan, alright, arctan y over x minus root 6 over root 2. Y over x. Look over here. Square root of 6, let's minus it out and divide by square root of 2. I get a minus 1.73 or tan. I got an inverse tan, I get a minus 60. What does minus 60 mean with reference to our quadrants? We're going 60 degrees down from 0 or 60 degrees down from 360, which means we're talking about 360 minus 60 or 300. And you know 300 here means 5 pi over 3. So we have everything now to convert this into our trigonometric form. Remember, the trigonometric form is this. R multiplied by cosine theta plus I sine theta. And we know our R now, it's 2 root 2. We know our cosine, it's 300 degrees, which is 5 pi over 3 plus I sine 5 pi over 3. The trigonometric form or the polar form. This 5 pi over 3 and this 5 pi over 3 are synonymous to this minus pi over 3 and this minus pi over 3, because I've shown you minus pi over 3 means you are going on your coordinate system minus 60 degrees in this direction. See, minus 60 degrees in this direction to yield you 300 degrees. When you get that 300 degrees, it is synonymous with 5 pi over 3. So whether you write cosine minus pi over 3 or cosine 5 pi over 3, it's the same thing. And whether you write root 8 over here or 2 root 2, here it's the same thing. But this form right over here is exactly the same as this form over here. So in this example, I showed you going from the polar to the basic form and then going back from the basic form to the polar form. So now you know each form is easily interchangeable depending on you knowing the modulus and argument. Let's dive into the main aspect of this video now. In the remainder of this video on complex number operations, for the interest of space, I'm going to be showing you quite a few things. Our goal over here is to show how you can multiply and divide two complex numbers. You know z1 and z2 represent complex numbers, and you know you can also say z1 is equal to x1 plus iy1 and z2 is equal to x2 plus iy2. You can say yi or iy, it's interchangeable, it doesn't matter, but this is what I'm talking about here. And you know each of these complex forms can be converted into its trigonometric or polar form. But our goal over here is to use the polar forms, the trigonometric forms. Now that we know how to convert this into this form, we're looking at operations involving z1 and z2. z1 is an independent polar form of some complex number, and z2 is another independent form of another complex number. Our goal is to learn how we do z1 times z2 and how we can do z1 divided by z2. That's our goal for this video, to show how you can multiply and divide these complex numbers in these two specific operations, because this will be important for the next video as we go through a special theorem on complex numbers. I'm going to take some space over here to show you each of these will have a specific formula which will come out. We will derive that specific formula for the multiplying part and the quotient part, and then we'll use those two specific formulas through a set of examples. The first thing we want to learn is how to do the multiplying part, z1 times z2. So this is where things can get a little messy in terms of space. If z1 times z2 is exactly equal to this top line multiplied by this second line, so let's do it. We have r1 cosine theta 1 plus I sine theta 1 multiplied by r2 cosine theta 2 plus I sine theta 2. Of course, when we're talking about the first complex number, we have 1's in here, and the second complex number has the 2's in here. It makes sense. The next step is easy. Just bring the r's, the modulus together. You get r1 and r2. Alright, that's done. Now you have the arduous task of multiplying these parenthesized aspects. Remember, using the FOIL, this will multiply with that, that will multiply with that, then you'll do the inner multiplying with each of these terms. So you have to do all of that. So let's start doing it. You'll have cosine theta 1 will multiply with this and give you cosine theta 1 cosine theta 2, then this will multiply with this term right here. You'll get, and I'm going to write the I sine components first, nothing wrong with doing that, with cosine theta 1 plus this with that, I sine theta 1 cosine theta 2, and lastly this with this right here. You'll get plus I square. You see this I will multiply with this I to give you I square, and then this sine theta 1 with this sine theta 2 to give you sine theta 1 and sine theta 2. Like I was saying, it can get a little messy. Now your task here is to separate the like terms. The like terms are these two intermediate terms, you know, like a square plus b square plus 2ab. These are like your 2ab terms, the intermediate terms. And these two here are your a square and b square terms. Because this I square is equal to a minus 1, you'll eliminate the I over here. So these two are your like terms and these two are your like terms. You have to combine them separately, but combine them. So you have r1 and r2. Let's bring these two like terms together. This I square is equal to a minus 1, so it will minus this out. You get it cosine theta 1 cosine theta 2 minus, remember I square is equal to a minus 1 with that, we'll minus it out, minus sine theta 1 and sine theta 2. Now look what I'll do. I'm going to parenthesize this part separately. Now look here, this plus sign, I'm going to bring this plus sign, I'm going to create a new set of parentheses for these two terms over here. All you got to do, you can't really combine them in any more than just writing them together. So let's just do that. And I can isolate an I from here. See, both of these have I, so let's isolate the I. Then you write everything else as you said. Sine theta 2 cosine theta 1 plus sine theta 1 and cosine theta 2. Remember, right now we're trying to determine the formula for the z1 and z2 operation of multiplying these two complex numbers. Now it's not too hard. You got to think back to your trigonometric identities, especially the sum and difference identities. Look over here. Cosine x, cosine y minus sine x, sine y looks something like cosine x plus y, doesn't it, right? You have cosine theta 1 plus theta 2. Think back to that trigonometric identity. Cosine x plus cosine y is equal to cosine x, cosine y minus sine x, sine y. Using the same identity. I've done that over here. Now think similarly for the product form identity, but using the sign. Sine x, sine y plus sine y, sine cosine x was equal to, sine x, sine x, there's like tongue teasers going on here. Sine x cosine y, sine y cosine x is equal to the same thing as sine x plus y, except here instead of x's and y's we're using theta 1s and theta 2. Look over here. We're very close to being done. And actually we are done. So this right here represents the formula for the combined product operation of two complex numbers. Z1, Z2, Z1 representing complex number 1, Z2 representing complex number 2 is equal to R1 times R2 times the cosine of theta 1 plus theta 2 plus I times the sine of theta 1 plus theta 2. When I show you these in example formats, it will make sense. Right now we're showing you the derivation of this. So this right here is the product formula derived. Let's look at the quotient formula next. The division of two complex numbers will yield a specific formula using many of the same techniques I just presented and the identity, but we'll get a slightly different formula, and we want to see what that formula is. So just look at what you have over here. Z1 is what? It's R1 cosine theta 1 plus I sine theta 1 divided by R2, and then you have cosine theta 2 plus I sine theta 2. You can individually separate R1 and R2 and just say R1 or R2. Now what you have to do is a process called rationalization. You got to rationalize this to eliminate the denominator. Remember, you can rationalize radicals, and as I've shown you in the previous video, you can rationalize complex numbers. You're going to rationalize it by taking the conjugate. You're going to use conjugates over here. Watch. You're going to get on the bottom cosine theta 1 plus, this is theta 2 plus I sine theta 2. You're going to multiply this with its conjugate, cosine theta 2 minus I sine theta 2. This is just the denominator part. Now we have to look at the numerator part. I'm going to take this, and of course I'm going to multiply by exactly the same thing. Okay? You're going to get cosine theta 1 plus I sine theta 1, multiplying this of course with the conjugate from the denominator, the conjugate. It's cosine theta 2 minus I sine theta 2. I hope you are seeing all of that. Let's look over here and bring it down over here. We still have the R1 over R2. Let's focus now purely on the denominator. Why? Because it'll be easier. Look over here. We're going to get no intermediate terms. You have a plus b times a minus b. The intermediate terms will go away. Let's look at these two items, and then let's look at those two items. Cosine theta 2 multiplied by cosine theta 2 will give you cosine square theta 2. You're going to get no intermediate terms because of the plus and minus. Any intermediate terms will cancel out. You'll have I sine theta 2 multiplied by minus I sine theta 2. You'll get minus I square sine theta 2. Now we have to look at the top part, which is going to be slightly long. FOIL method, of course, all the way across. You'll get on the top cosine theta 1 cosine theta 2 minus I sine theta 2 cosine theta 1 plus I sine theta 1 cosine theta 2. Nothing's going to cancel out over here, as you will see. Minus I square, we're right here, this multiplying with that, minus I square sine theta 1 and sine theta 2. It can get messy, but this is why you have to know trigonometric identities, because they'll play out. Look over here. I square is equal to a minus 1. Minus 1 will hit with this minus right here, make it a plus 1. What do you end up with? You end up really with and I've forgotten the square over here. These two signs over here would have multiplied with each other to give you the sine square. But you have a trigonometric identity here. Sine square x plus cosine square x, x and theta interchangeable, is always equal to 1. So all of this on the bottom becomes a 1. You can cancel all of this out using the Pythagorean identity and make it equal 1. All you're left now is with the task of the top. Simplifying the top, and you'll do it exactly the same way as we did the previous derivation, the product one. Look over here, like terms. Here's a like term right over here. This and this will be your like terms. Everything which is not circled in between are your other bunch of like terms. You have on the top, I have eliminated the fraction by bringing in over 1 over here. So let's just write everything as this. Cosine theta 1, cosine theta 2, right? We can separate this and bring it with this. Minus I square is really same thing as saying minus 1, because I square is a minus 1. This minus 1 will multiply with this minus, will become a positive. See? Positive. Sine theta 1, sine theta 2. This is my first bunch of things isolated and brought together. Now look over here, we have a minus here, but we have a plus here. I want to keep everything as a plus. I'll show you why. What do we get over here? We get a minus. Let's isolate an I actually over here. We have an I here, an I here. Let's isolate the I. So what do we get over here? We'll get a minus sine theta 2 cosine theta 1. Look over here. You'll get a plus sine theta 1 cosine theta 2. All you're left now is with the task of bringing all of this together using your sine and cosine sum and difference formulas. R1 over R2. Over here, cosine x cosine y plus sine x sine y reminds me of this version of the cosine sum and difference formula. Cosine x minus y, x minus y. Now look over here, I have a plus I over here. Plus I, and now I have to marry up the sine terms using their formula. I have a sine theta 2 here, but I have a sine theta 1 here. I'm going to use a theta 1 first. You can write all of these, flip it around the plus sign. You can say over here you have a sine x cosine y minus sine y cosine x, which reminds you of the what? Sine x minus y sum and difference formula. So you're going to put over here theta 1 minus theta 2, and you will be done. You have the benefit here of seeing all of this in still and see exactly what I've done. I may have tongue twisted a bit of words over here as I was writing them, because there's a lot going on here, but once you still this and the previous one, you can see exactly what has happened over here. It involved the trigonometric identity, the sine and the cosine sum and the difference identities, and involved the Pythagorean identity. But at the end you end up with the formula. Just compare this to the product formula. In the product formulas you had pluses all the way across. In the quotient formula, you bring the minuses here in terms of the theta 1 and theta 2, but you still retain the positive in between. So you can see in the previous still the z1, z2, and in this still z1 divided by z2. So these two formulas, which I will lay out clearly as we do some examples, are what you need to be aware of. Okay, so this is where it actually becomes fun now. You know, I've up till now shown you how we derive the z1 and the z2, multiplying the two complex numbers, and the z1 divided by z2, dividing the two complex numbers, the formulas associated with each of those. But look over here, very clearly the formulas are laid out for each. It's always R1 times R2 and the rest, or R1 divided by R2 and the rest. But look specifically here in the actual parenthesized portions. In the product formula, everything is a positive. You have cosine theta 1 plus theta 2 plus I sine theta 1 and theta 2. But in the quotient formula, you get some minuses show up. You have cosine theta 1 minus theta 2, but you still retain the positive in here. So our goal for the remainder of this video are to show you examples where we're either multiplying or we're dividing these complex numbers. This right here is this question which is laid out where z1 represents this complex number, and these are pi's over 3's, pi over 3's, and then z2 is this complex number with a pi over 6 involved. And your goal here is to, or your task is to multiply the two numbers. When the question is laid out in this form, it's actually the easier version of the question, because here the complex numbers are already identified in the trigonometric or the polar form. You see, both of these are the polar forms. You're already given the polar form in here. for this question, so the question is actually easy. All you gotta do is put the polar forms into the formula, the correct formula, and you proceed. And you know we have to do z1 times z2, so take the r values and multiply them. So you're gonna get z1 times z2 is equal to 3 times 4, which is 12. Now you're going to do just put the cosine, run the formula through. Cosine of the two representative angles, pi over 3 and pi over 6. Pi over 3 is a 60 and 30, 90, pi over 2. You could do this on the calculator. I'm just, for the interest of time and space, I'm trying to skip some steps over here. Pi over 3 plus pi over 6 again is a 90. And it's pretty much easy from here. Cosine of 90 is always a 0. Sine of 90 is always a 1 plus I. What are you going to end up with? Getting a little sloppy over here. You're going to end up with 12 times 0 plus 12 times I. You'll get 12I. Not hard at all, is it? Perhaps the derivation of these is more messy and hard than the actual application via these examples. But this look over here was an easier type of question because the question involved an operation where you were given the trigonometric forms of your complex numbers. The rest of the questions I'm going to show you in this video is going to involve the extra step first, because we're not going to be giving you the questions in the trigonometric form. You'll be given questions in the complex number format, and then you have to do the extra step of converting into the polar quadrant trigonometric form, and then you actually carry out the operation. Okay? So look for these slight changes as we go through the rest of the examples. So here's an easy example, but like I said, it's going to be slightly harder than the previous one because look, you're given the z1 and the z2, z1 and z2 in their basic forms. You don't even have the complex form in terms of the polar aspects or the trigonometric aspects. So what we have to do is actually determine that, and then we proceed from there. If this represents z1 and this represents z2, write these out in their basic coordinate forms. This is really like saying 2 comma 2, and this thing right here is the same thing as saying 1 comma minus 1, right? Do a quick graph over here. 2 comma 2 is going to be right over here. 2 and 2. 1 comma minus 1 is going to be right over here. 1 and minus 1. What's your r going to be over here? Remember, the modulus is always a square, sum of the squares of the two components and then the square root of that. You're going to get a 2 root 2. 2 square plus 2 square is a root 8, which will give you a 2 root 2. What's the r over here? It's going to be a root 2. 1 square plus 1 square, square root of that 2 will be a root 2. Find the theta over here. You know, by graphing it out, you know you're dealing here with a quadrant 1, here you're dealing here with a quadrant number 4. See, plotting it out in this complex plane clues you into which quadrant you are, because that will guide you towards your angle. 2 divided by 2 is going to give you a 1. Inverse tangent of that 1 will give you a pi over 4. You know you're dealing here with a 45-degree angle, pi over 4. What about here? You're dealing with a minus 1. Minus 1 divided by 1 is a minus 1. Inverse tan of the minus 1 will give you a minus pi over 4. But minus pi over 4 is synonymous with 7 pi over 4. Remember, you're going 45 degrees down of 360. 360 minus 45 will give you 315, which is 7 pi over 4. Now, you have to write these in their trigonometric forms, polar forms, because once you have them in your polar form, you can actually carry out the operation. Let's write the polar form over here. The z1 will be represented by 2 root 2, which is your r value, cosine pi over 4 plus I sine pi over 4. This is my z1. What about z2? Let's do it here for the interest of space. z2 is equal to root 2 cosine 7 pi over 4 plus I sine 7 pi over 4. The polar forms of both of these complex numbers is presented before you. Now we have to actually carry out the operation. What's our operation? These two are multiplying. You see, they're multiplying. You have to find z1 and z2. You got to find this. z1 and z2 is not going to be hard. You're just going to put everything in this formula over here. Here's my r1, here's my r2. See, r1 and r2, 2 root 2 times root 2 is going to give me a 4. Now we have to add the angles. Pi over 4 plus 7 pi over 4 is going to give me 8 pi over 4, which is a 2 pi. See, 45 plus 315 gives you 360. Cosine of 360 plus I sine, of course, exactly the same. Sum is obtained over there. Now you got to open it up. Cosine of 260 is always a 1. take that on your calculator. 360 and cosine and you get a 1. Sine of a 360 is a 0. What you end up with at the end is just a 4. So the product of these two complex numbers z1 and z2 gives you a final answer of 4. And that's a good and correct answer. We'll run through more examples for the rest of this video so you can make all of this very clear. But you can see the process. You'll individually dissect the two complex numbers into the trigonometric forms. The trigonometric forms will then be carried out using the correct operation formula. Now my question over here is 5 divided by 2 plus 3i. These are two complex numbers but in a divide aspect. You want to be looking at this in this terms always. X plus yi. Alright, just look at it in that. So you're going to rewrite the top as 5 plus 0i. And then of course on the bottom you have 2 plus 3i. Break these into their individual components. You know, this right here is my z1, this right here is my z2. And we have to determine over here z1 divided by z2. Because the question already involves a divide. So we have to determine z1. The quotient of both of these is what we have to determine. So z1 can be represented as 5 comma 0. Remember x comma y, x and a y, the real part, the imaginary part. And let's graph it out. 5 comma 0 is going to put you right over here. The r value here automatically will be 5. And the theta value here will actually be 0 degrees. Right? 0 degrees. It's on x-axis line. 0 degrees. And the distance, remember modulus is the distance from your point to your origin. Here it's 5. You could do 5 square plus 0 square and square root and you'll get the 5. Let's look over here at this other z2, which is 2 plus 3i. Graph them out. 2 plus 3i is the same thing as looking as 2 comma 3. 2 this way, 3 up this way. Right? 2 here, 3 here. What's my r going to be? 2 square plus 3 square, square root. Root 13. I believe it's root 13. 4 plus 9 is a root. 9 is a 13 and square root of that. Theta is going to be arctan. Alright, arctan of 3 over 2. We'll probably get a decimal answer over here because we don't have a trigonometric ratio involved here. Let's use our calculator. 3 divided by 2 inverse tan. I get a 56.3. There's nothing wrong with getting decimals in your answers. 56.3 degrees. Write these in their polar forms. The first one, polar form, as you know, the formula for that is r, which happens to be 5 times the cosine of the angle here, which happens to be 0, plus I sine the angle is a 0. We can use extra parentheses if you want to make things more delineated. Look at this one over here. What's my r over here? Right, the polar form will be root 13, which is the r value times cosine 56.3 plus I sine 56.3. 56.3. Here are my two polar forms. I have to now actually complete the operation. The operation is going to be r1 aspects, or the z1 divided by z2. What z1 is 5 and z2 is root 13. You can do 5 over root 13. Okay, and now we have to do the actual formula. You're going to be minusing the angles over here. What's a 0 minus 56.3? It's going to be minus 56.3, right? Minus 56.3. You can actually convert minus 56.3 into a proper answer. 360 minus 56.3, because you're going 56.3 degrees south or down of 360 degree, or your 0 axis horizontal, and you have 303.7. You can use 303.7 or you can use minus 56.3. It don't matter. Plus I sine minus 56.3. Now all you gotta do is carry it out. What's cosine of minus 56.3? Will be the same thing as cosine of positive 56.3, which is a 0.5548. Okay, so we have 5 over root 13. Here we're getting a 0.5548. Let's see what we get over here. I think we're going to get a minus over here because these are going to be fourth quadrant angles. Sine is always minus. 56.3 minus, sine it, and you get a minus 0.8312i. You can open all of this. You're going to have to get a decimal answer of 5 divided by root 13. 5 divided by root 13 gives me a 1.38. You got to multiply 1.38 individually with all of this. Times 0.5548, I get a 0.769. 0.769 minus, and over here for the last part I get minus 1.15 1.152i. Here is my answer. The division of 5 divided by 2 plus 3i, these two separate complex numbers, gives you this as your final answer. 0.769 minus 1.1521. It wasn't a hard question, just you had decimals come in, which kind of complicated your calculations, but the process was exactly the same. Let's run through some more examples. So here's a question we have to do. Find the product of these two complex numbers. This is my z1, this is my z2. Again, write these in their common forms. Minus 2i is the same thing as viewing as 0 minus 2i. And of course 1 plus i stays as 1 plus i. Break these down into their complex planes. 0 minus 2i is the same thing as 0 comma minus 2. 1 plus i is the same thing as 1 comma 1. Plot them out. 0 comma minus 2 lands you over here. 1 comma 1 lands you here. R over here is of course going to be 0 square plus minus 2 square root of that, and you'll still maintain your 2. But you know you have 0 comma minus 2 is throwing you directly on the y-axis, and here by now you should know it is 3 pi over 2 or 270 degrees. 270. 0, 90, 180, 270. 3 pi over 2 is 270. Let's look over here. X is 1. Y is 1, therefore R must be 1 squared plus 1 squared square root, root 2. And we know we're dealing here with a trigonometric ratio of 1 and 1. If you do arctan of 1, 1 divided by 1 is 1. If you do inverse tan of 1, you get a pi over 4, which is a 45 degrees. Write them out in their polar forms. Polar form over here will be 2. You can say z1 is equal to 2. Remember with the polar form, cosine 3 pi over 2 plus I sine 3 pi over 2. We have a lot of things playing out here from the previous video where you actually, for each question, deriving the polar form. But that's fine, it's all practice. z2, our second number, will be root 2 times cosine of pi over 4 plus I sine pi over 4. Remember all of this. This whole stuff will play out in the next video again, but in a next more advanced format as we determine roots. Now all we have to do is determine z1 times z2 using this formula here on the top. What's r1 times r2? 2 times root 2 is 2 root 2. Then you're going to add these angles because in the product formula you have addition playing out. 3 pi over 2 plus pi over 4 is 270. 270 plus 45 is 315. Cosine 315 plus I sine 315. You know 315 is an easy angle because it's one of your trigonometric ratios. It's a 45, 90 degree angle, but it just happens to be in quadrant number 4. It's not hard to determine what that is. It's going to be 2 root 2. You can always use a calculator if you don't want to run these three things through your head. Cosine of 315 will be the same thing as saying 1 over root 2. Sine of 315 will be the same thing as saying minus 1 over root 2, but that minus is going to affect the sign and make it a minus I over root 2. Okay? Open everything up. When you open everything up, these root 2's and root 2's will cancel out. You'll get on the top 2 minus 2i. 2 minus 2i. A good and correct answer. Remember, if you don't recognize or understand the concept of those trigonometric ratios I keep mentioning in each of my videos, there's nothing wrong with you using the calculator. Look over here. 315 cosine multiplied by 2 and root 2. Multiplied by 2, multiplied by root 2. And what are you going to get? You'll get a 2. And you can do the same thing with the sine aspect and you'll still get 2. You'll get a minus 2 though, but you'll still get the numeral 2. Focus your attention on this question over here. We have to find the quotient of this operation over here. z1 on the top, z2 on the bottom. So this right here is my z1 and this right here is my z2. First thing you want to do is separate them into their coordinate forms. 3 plus 4i is the same thing as 3 comma 4. 1 minus I root 3 is the same thing as 1 comma minus root 3. The only reason why I recommend you do this because it clues you in into which quadrant you're dealing with, which clues you in into what type of angle you'll have. 3 comma 4 is quadrant 1, and you know you do 3 here, 4 here, 3 here, 4 here, and you determine R. It's going to be a 5. 3 squared plus 4 squared, square root of that, 25 is a 5. In theta, you're going to have to do this with a calculator. 4 divided by 3 is always y divided by x. Inverse tan, I get a 53.1. Okay, my theta is 53.1. Let's look at this other one. 1 comma, minus root 3. It clues you in into the fourth quadrant. You're going 1 here in the x-axis and you're going minus root 3 down. Alright, 1 minus root 3. You got to determine the r. The r is going to be 1 square plus 3 root 3 square and square root of that. It's 1 plus 3 is a 4, square root of 4 is a 2. Theta. Now this right here is one of your trigonometric ratio angles. 1 and root 3 can only come from a 60 degree angle, because 60 will oppose the minus root 3 and the 30 here will oppose the 1, and you know you can have a 2 over here, 1 root 3 2, a 30 60 90. So we know our angle over here is going to be a minus pi over 3, which is the same thing as saying 5 pi over 3. Why? If you don't understand that, look over here at your calculator. Do inverse tan of root 3 minus and divide that by 1. Let's do 3 square root minus divided by 1 and inverse tan it, I get a minus 60. Minus 60 plus 360, which is your reference angle, here is your horizontal, plus 360 will give you 300 degrees, which is 5 pi over 3. Now we just have to write these in their polar forms. The polar form for this z1 is going to be 5, which is r, cosine 53.1 plus I sine 53.1. What about z2? z2 over here is going to be r, which is 2 cosine 5 pi over 3, which is 300 degrees, plus I sine 5 pi over 3. You could have written here 300, or you can write 5 pi over 3. You can even put minus 60 over here and it'll still be fine. Now you got to run it through the divide formula. Remember, we're dividing over here. So r1 divided by r2 is what? 5 over 2. 5 divided by 2, which is a 2.5. Now let's individually minus these angles. 53.1, look, 53.1, which is your 1, your theta 1. 53.1 minus 300. Minus 300 is a minus, you're going to get a cosine of minus 246.9 degrees. Plus I sine, of course, you'll get the exact same thing, 246.9. All you gotta do is do the calculator computations. Do this with this and do this with that, and you're done. Do cosine of minus 246.9. 246.9 minus cosine it and multiply by 2.5. I get a minus 0.98. That's my real number term over here. Minus 0.988. Remember, the first part of a complex number is your real part, and the second part is always your imaginary part. I believe this is going to come out as a positive answer. Let's do minus 246.9, sine it, because this ends up in being quadrant number 2. You sine it and you multiply by 2.5, you get a 2.29. Let's round that up to 2.3i. So our answer is really 0.988 plus 2.3i. Minus 0.988 plus 2.3i. It looks good to me. I want to end this video with this next question. It will be our last. So our question here is to find the product of these two complex numbers, minus root 3 plus I times minus 1 plus I. This here is my z1 and this here is my z2. Again, split them up into their coordinate forms. This is a minus root 3 comma 1. This right here is a minus 1 comma 1. Then you want to graph them out. Remember, we have to convert these basic forms into their trigonometric forms, and from there run them through the appropriate formula. Minus root 3 comma 1. We're talking here about quadrant number 2. Minus root 3 this way and then 1 up this way. Minus root 3 and 1. You know, we're looking here at a 30, 60, 90 degree angle. But anyhow, let's look at this. Minus 1 this way and 1 up this way. So now we're looking at a 45, 45 and a 90 degree angle. 1 minus 1, and you know there's going to be a root 2. Our R value here is going to be a 2. You could have done minus root 3 square plus 1 square and square root that, you'll still get a 2. And here your R value will be a root 2. Minus 1 square plus 1 square, square root, you'll get a root 2. We got to determine our angle here. Determination of angle is always arctan y over x. But sometimes you don't have to do that because you can recognize trigonometric ratios. I'm seeing a ratio over here of a 30, 60, 90 degree angle. And here's my tangent. Opposite that is a 1. It must have been a pi over 6. 30 degree angle, pi over 6. Look over here. 1 divided by square root of 3 and minus inverse tan, I get a minus 30. But this minus 30 is now with reference to your 180 degrees. So it actually represents 150 degrees. Alright, 150. minus 30, but up from this 180. 180 minus 30 is 150. So it's a pi over 6, a 30-degree angle. Let's look over here. We're looking at it. Inverse tangent of a minus 1, but in the second quadrant. So this is going to be a minus pi over 4, a 45-degree angle in the second quadrant, which will be 135, which will be 3 pi over 4. So we have everything we need now to determine our polar forms. For the first one, Z1, our form is 2 multiplied by cosine of 150. I'm now using the numbers, not the radian format. Plus I sine 150. You could have used the radians. You could have done here 5 pi over 6 instead of 150. 5 pi over 6 is 150 degrees. What about this Z2? Z2 over here is going to be root 2, which is your R value, times cosine of 3 pi over 4, which is 135, plus I sine 135. Remember, the real part, the imaginary part of this complex number. We got to run it through the appropriate formula, Z1 times Z2. That's what we have to do, Z1 times Z2. What's our R1 times R2? 2 root 2. And when you're doing these product versions, you add the numbers. 150 plus 135 gives me 285. Cosine of 285 plus I sine of 285. These are all in the fourth quadrant. Remember, this right here is 270, then 15 degrees here will be 285. So these are all fourth quadrant angles. But you can do all of this and get a decimal answer. I'm going to do 2 root 2, and I'm going to save that in my memory. 2 multiplied by square root of 2 is 2.828. Then I'll individually multiply in here and present your final answer. 285 cosine will be positive. Multiplied by that 2 root 2, I get a 0.732. 0.732. I'm going to get a minus over here because sine is always minus in the fourth quadrant. 285 sine multiplied by my memory recall value here, 2 root 2, is a minus 2.73. Minus 2.73 I. Here's my final answer for the product of these two complex numbers. Remember, it's a process. The process, of course, is more cumbersome when you're actually deriving these two individual formulas. It can get messy, but the actual application is not hard. You have to when given these forms, you have to determine in terms of the complex plane your polar and the trigonometric forms. When you have the polar or the trigonometric forms, you run them through the appropriate formula and you actually determine your final answer. It can either be Z1 times Z2 or it can be Z1 divided by Z2, but the rest is all easy, and even though it's elaborate, it's not very hard, it's still easy. I hope you enjoyed this video. It may have been a pretty long video, but I hope you actually enjoyed this one. Please like, subscribe, and share. Thank you for watching this video. Have a nice day.